So far we have studied what we mean by vector spaces and what we mean by vectors. To recapitulate, a vector space is a collection of objects called vectors, and this collection satisfies some basic properties, and the important properties for in a vector space are that it is close to addition and scalar multiplication. So, when you add two vectors you get another vector, and when you multiply a vector by a scalar you get another vector. So, the axioms of a vector space are related only to addition and scalar multiplication. Okay. So, the axioms of the vector space do not talk about the product of two vectors or multiplying two vectors, and this is the next topic that we will talk about. So, vector multiplication is it is not necessary for a real vector space that you need to define multiplication of vector space of vectors. However, there are spaces called real inner product space, and these are spaces where an inner product of two vectors is defined. So, these are special kinds of vector spaces. In addition to this, we will look at three kinds of products of vectors. The first is called the dot product or the inner product, the second is called the cross product, and the third is called the direct product or the tensor product. Okay. So, let us look at real inner products spaces, and this is the first kind of product, which is called the inner product or the dot product. You all probably know how to take the dot product of two vectors in say three-dimensional Cartesian coordinates. So, in three-dimensional Cartesian coordinates, if you have a vector v1 denoted by x1 I plus y1 j plus z1 k, and you had a vector v2 denoted by x2 I plus y2 j plus z2 k, then the inner product of these two vectors is denoted by v1 dot v2, and the inner product of these two vectors gives you a scalar, and the value of the scalar is x1 x2 plus y1 y2 plus z1 z2. Okay. So, thus we say that inner product of two vectors yields a scalar. And for this reason, this is also sometimes called the scalar product. So, it is called the scalar product, inner product or dot product, and this is the procedure for taking the inner product of two vectors in three-dimensional space. Okay. However, this procedure is restricted to vectors in Cartesian coordinate system of 3 or more dimensions or even 2 dimensions. However, we want a more general definition of an inner product. Okay. So, in a more general a very general definition of inner product, general definition of real inner products. And I use the term real because we are dealing with real vector spaces, and in a real inner product space, the inner product will be a real number. So, the inner product is denoted by the inner product of two vectors v1 and v2 is generally denoted by this bracket. So, this is a notation for inner product of two vectors v1 and v2. and this is a scalar or a real number. Now this is defined for any two vectors, and you can have, depending on the vector space you are considering, you can have the appropriate definition of the inner product. In fact there is no unique definition of inner product, and you can define many inner products, and any product that satisfies two conditions is a valid inner product. The first condition is the inner product is commutative. So, V1, so the inner product of V1 and V2, this is specific to a real inner product. So, inner product of any two vectors is equal to the inner product of the same of the two vectors in the taken in the opposite direction. So, for example, in this case you can clearly see that if I take V2 dot V1, then I will get x2 x1 plus y2 y1 plus z2 z1, which is the same as x1 x2 plus y1 y2 plus z1 z2. Okay. Then the second condition is that the inner product of any vector with itself. So, if I take a vector V1 with V1 should be greater than or equal to 0, okay. And V1 dot V1 is equal to 0 if and only if V1 is a 0 vector. Okay. So, the only case when the inner product of a vector with itself can be 0 is if the vector is the 0 vector, and the 0 vector we had mentioned that this is a vector in the vector space such that you add any vector to it, you get the same vector. Okay. So, we can define the inner product of two vectors, and any product defined so that it satisfies these two conditions is a valid inner product. I will be using two symbols for the inner product. I will be using either this symbol, or I will be using the symbol V1 dot V2. Okay. This is not restricted to 3 dimensions. We will see that we will see how we can extend this concept of inner product to other kinds of vector spaces. Okay. In addition to this, I have not stated in the formal definition of the inner product has some other conditions regarding associativity and distributivity, but I have not stated them here, and I will assume that they are satisfied by the inner product that you are considering. Okay. Okay, so let us look at some examples of inner products. The first example is the usual dot product. So, before we go to some examples of inner products, I want to mention what we mean by a real inner product space. A real inner product space is nothing but a vector space for which you have defined an inner product. So, a vector space for which the inner product is defined is called a real inner product space. Okay. So, now let us look at some examples of inner products. Example 1 is the usual dot product of vectors in 3D Cartesian coordinates. So, for example, you can say V1 is equal to x1 y1 z1, V2 is equal to x2 y2 z2, then the inner product is equal to x1 x2 plus y1 y2 plus z1 z2, and we have seen that this satisfies the axioms for a real inner products for a real inner product. The second example, so this is an inner product in the 3D Cartesian coordinates as in the 3-dimensional vector space, and so the 3-dimensional vector space with this definition of the inner product forms a real inner product space. The second example is suppose you had the vector space of all real functions of a single variable. So in the last class we saw that the space of all real functions of a single variable, the f of x, where f of x can be any function of a single variable. It can be polynomial, it can be trigonometric, it can be exponential, it can be an exponential of a logarithm, it can be any function, and this forms a vector space. Okay. And if you look at this vector space, then we can define an inner product, inner product of f and g of x. So, f of x and g of x are two functions of x. So, both these are members of this vector space. Now, we define the inner product of f of x and g of x in this form: f comma g is equal to integral f of x g of x dx, okay, over the range of x. So if this is defined from minus infinity to plus infinity, if x goes from minus infinity to plus infinity, then this would be the range of integration of this. So now the question is this a valid inner product? So, in order to verify that this is a valid inner product, you will see if it satisfies the axioms of an inner product, and the first axiom is f comma g should be equal to g comma x, g comma f, and you can clearly see that I can always write this integral in this form. I can always switch the order of f and g, and so I can write the integral in this form. And if you look at this and look at the definition of f comma g, you will see that this is the definition of g comma f. So, clearly f comma g is equal to g comma f. Inner product of f and g is indeed commutative. The second property that we have to ensure is that f comma f is greater than or equal to 0, and if you look at from this is integral minus infinity to plus infinity f of x square, f of x, I will write it this way, dx, okay, f of x square dx. And now what you have is that the integrand is positive at each value of x. So, clearly this is greater than or equal to 0, and it is only equal to 0 when f of x is equal to 0. So, the point is that f of x can have both positive and negative values, but the square of f of x is always non-negative. So, it is always greater than or equal to 0, and so this integral will be greater than or equal to 0. Okay. So, we can see that this definition of inner product is a valid definition. Okay. And now we can construct an inner product space of functions of a single variable x, and this inner product space is closely related to the Hilbert space that you will see in your quantum chemistry courses, and therefore it is good to be exposed to this sort of thinking. Okay. Now, this definition of inner product, so we have defined the inner product in terms of two basic axioms. One is that it should be commutative, and the other is that its norm, or the inner product of a vector with itself, should be greater than or equal to 0. Now, the inner product of any vector with itself, okay, this the square root of this quantity is called the norm of the vector, norm of v, and it is denoted by v. Okay. So one of the conditions of the definition of inner product is that the norm should be greater than or equal to 0. Okay. So now this definition of inner product immediately implies two properties of inner product, and the first property is that inner product satisfies Schwarz inequality. So any inner product will satisfy the Schwarz inequality. Any real inner product which satisfies the two axioms of real inner product space will also satisfy the Schwarz inequality. So the Schwarz inequality says that inner product of two vectors v1 and v2 is always less than or equal to square root of inner product of v1 with v1 times the inner product of v2 with v2. In other words, it is less than or equal to the norm of v1 times the norm of v2 times norm of v2, and this is called the Schwarz inequality. This is true for any inner product space. So we looked at two very different looking examples of inner product, and I leave it as an exercise to you to try to show that indeed both these vector spaces satisfy the Schwarz inequality. Okay. The second axiom, the second property that they satisfy, and actually it is not just one property, there are a whole series of properties that follow from this one, is called the triangle inequality, and this states that the norm of v1 plus v2 is always less than or equal to norm of v1 plus norm of v2. So the way to think of this is, I mean if you imagine, it is called the triangle inequality. If you imagine v1 and v2 to be vectors in the usual 3-dimensional space, then v1 might point in this direction. So if this is v1, this is v2, okay, then v1 plus v2 will be this v1 plus v2. So this is called the triangle inequality because the norm of this vector, and the norm is directly related to the length. So the length of this vector is less than the sum of lengths of these two vectors. So in other words, the length of one side of a triangle is always less than the sum of the length of the other two sides. So this is a generalization of this to other vector spaces, gives you something called the triangle inequality. Okay. Now based on the triangle inequality, there are other geometric inequalities which are related to the triangle inequality called the parallelogram inequality, but we will not mention it here. Now I leave it as an exercise to you to also look up the proofs of these inequalities, so you really understand what is meant by these inequalities. Okay. Now the inner product is extremely useful in all of coordinate geometry, but in addition the inner product is a quantity that is very widely used in quantum chemistry. Okay. The inner product allows us to define something called a projection. Okay. So a projection, if I had a vector v1 and a vector v2, okay, then I can define something called the projection of v2 on v1. So projection onto v1 of the vector v2. Okay. So this is called projection of v2 onto v1. Okay. So I am using this symbol for the projection of vector of so you are projecting vector v2 onto vector v1. Okay. And this can be defined in terms of the inner product. So, I can define this as V2 comma V1 into V1 divided by norm of square. Okay. So essentially the way to think of this, you can think of this as two parts. The first part is you can think of this as V2 projected onto a unit vector in the direction of V1. So, that is V1 divided by norm of V1. Okay, so, this is the first part. So, it is an inner product of V2 with a unit vector in the direction of V1, but this gives a scalar and the projection turns out to be a vector. So, you want a vector in the direction of V1. So, you multiply by a unit vector in the direction of V1. Okay. So, the projection of one vector onto other is, if you had a vector V1 and you had another vector V2, then the projection is nothing but this. This is the projection. This is a projection of sorry, I'll do it the other way. I'll call this, you have V2 and V1. So, you want the projection of V2 onto V1. So, projection of V2 onto V1 is this vector. Okay. So, notice that it is a vector, it is in the same direction as V1 and it tells us something about the inner product of V2 and V1. Okay. So, if you think of the inner product of these two vectors, if these are two vectors in the usual Cartesian coordinates, then the inner product or the dot product is just V1, the absolute value of V1 times the absolute value of V2 into cosine of this angle, and V2 cosine of this angle is nothing but this length. Okay. So, the projection is nothing but this length multiplied by a vector in that direction. So, once again I want to emphasize that the projection that we defined, I try to explain it in terms of the usual vectors in three dimensions, but it is possible to define these projections for any inner product space. So, all you need, once you have the definition of inner product and the definition of a norm, you can always define a projection of a vector onto another vector. Okay. Now, so this is as much as I want to say about the dot product or the inner product. Now, the next kind of product, and this is something that you have seen, is called the cross product. Now, it turns out that the cross product is unique to three dimensional space. So, in that sense it is not as general as a dot product or an inner product, but it is unique to three dimensional space. In three dimensional space, if you have two vectors given by x1, y1, z1, and you had vector v2 given by x2, y2, z2, okay, then the cross product of these two vectors gives you a vector, okay, and that vector has three components, and the three components of the vector are given by, so the I component is related to y1 z2 minus z2 y1, y1. The j component, so the j component is related to z1 x2 minus x1 z2, and the k component is simply x1 y2 minus x2 y1. Okay. So, the cross product, notice that in the dot product you just had x1 multiplying y1 or sorry x1 multiplying x2, y1 multiplying y2 and z1 multiplying z2. In the cross product you have x1 multiplying either z2 or x1 multiplying y2. So x1 does not multiply x2, but it instead multiplies these two. Okay. So the cross product is different from the dot product in that sense, and it is unique to 3 dimensions because the cross product of two vectors, you need to have this anti-symmetrization possible, and that is possible in 3 dimensions. Okay. So I won't mention a lot more about the cross product, since I assume that all of you know how to take cross products. I will briefly mention a third kind of product, and the next thing is the direct product. And I am not going to talk too much about this because this is not as useful in the standard in usual MSc level chemistry, but in more advanced courses you will see this product appearing again. So the direct product of two vectors. So if you had vector v1 and you had vector v2, okay, then this yields an object called a tensor. Okay. So it yields an object called a tensor, and this is a tensor of rank 2. Okay. So what is the idea of the direct product? So here in the dot product we multiplied x1 by x2, in the y1 by y2, z1 by z2. So you multiplied the terms corresponding to the same component together. In the cross product you multiplied x1 by either y2 or z2. Similarly, you will always multiply y1 by either x2 or z2. So you always you multiply terms with of one component with another component. Okay, you never have any term with where the same component is repeated in this cross product. A tensor the direct product is something that combines both these, and it says that you can multiply, you look at all possible combinations of products. Okay. So if you look at all possible products that you can generate, then there are 9 possible products, and it is typically represented in this matrix form. Okay. So the 9 possible products are x1 x2, x1 y2, x1 z2, then you could have y1 x2, y1 y2, y1 z2, and you could have z1 x2, z1 y2, z1 z2. Okay. So notice that along the diagonals of this direct product you have the terms that appear in the dot product. So dot product is the sum of these diagonal elements, and the cross product is related to the elements that you see in the cross product appear here. Okay. But you go from 2 vectors with 3 components to an object with 9 components, and this object is called a tensor of rank 2. And it is called rank 2 because you have a row and a column, and essentially it is a direct product of 2 vectors. Okay. Now we won't talk much about tensors, but the one useful way to think about tensors is that these are objects that are generalization of the concept of vectors. So vectors, if you so in this scheme, a vector is a special case of a tensor, and it is a tensor of rank 2 of rank 1. So vector is a tensor of rank 1, and you can go ahead and you can say that even a scalar is a tensor of rank 0. So tensor is a generalization of the concept of vector. So we started with scalars, then we went to vectors, and you can go to tensors. And tensor is a generalization; it can have arbitrary ranks. Okay, and we usually in chemistry applications we usually restrict to tensors of rank 2, 3 or even sometimes 4. These appear in there are two prominent places where you will see tensors. One is the moment of inertia tensor, which appears when you are analyzing the rotations of a molecule. The other place where you see tensors is when you are trying to analyze nonlinear optical phenomena. So the two places where it appears, I will repeat again. One is the moment of inertia tensor, and this appears when you are studying rotations of molecules. The other is the nonlinear radiation matter interaction. And in nonlinear radiation matter interaction, which is essential to the development of lasers and other nonlinear optical phenomena, in that you have tensors corresponding to the polarizability and the hyperpolarizability of the medium. Okay. So we have seen that the product of two vectors can be defined in many ways, and we have seen at least three useful definitions of products. Okay. I will not talk about all the scalar triple product and vector triple products. These are simple extensions of the dot product and the cross product involving more than two vectors. The next concept that I want to discuss here is what is called as linear independence. And linear independence, and two related concepts are basis and dimensionality. Okay. So what is meant by linear independence? And first I will give the definition of linear independence, and then I will try to explain it with examples. This concept will become a lot more clear when we start discussing matrices, and there you will use this concept of linear independence very it's used very often in study of matrices or in solving a system of linear equations. Okay. So let us look at linear independence. What is the definition of linear independence? So the definition: a set of vectors v1, v2 up to n up to vn is said to be linearly in a set of vectors are said to be actually probably I should say the vectors v1, v2 up to vn are said to be linearly independent if they satisfy the following condition. Okay. So what is the condition they should satisfy? Whenever C1 V1 plus C2 V2 Cn Vn equal to 0, for scalars C1 C2 up to Cn, then C1 equal to C2 equal Cn equal to 0. Okay. So I will just go through this once again. A set of vectors is said to be linearly independent if they satisfy this following condition. The condition is that whenever you have a linear combination, I imply each vector is multiplied by a scalar, and then this vector is added to the next vector, and whenever this linear combination of vectors gives you the 0 vector, okay, for some scalars C1, C2 up to Cn, then the only way that is possible is if each of these is equal to 0. Okay. So what we are saying is that you have a set of equations and you solve for all the C1s and C2s up to Cn, and if your only solution that you get for this is a trivial solution where all of these are 0, then these vectors are said to be linearly independent. Okay. So in other words, this expression gives you a set of equations from which you solve for each of the C1, C2 up to Cn. Now it is clear that C1 equal to C2 equal to up to Cn equal to 0 is a valid is a solution which satisfies this equation. Now if there is no other solution, then these vectors are said to be linearly independent. Okay. So this is the definition of linear independence, and this is the definition. So if these vectors v1, v2 up to vn satisfy this property, then these vectors v1 up to vn are said to be linearly independent. So this is the definition of linear independence. If there exists some combination of where of C1, C2 up to Cn such that not all of them are 0, okay, that means you are saying that these set of solutions have a non-trivial solution, then these vectors are said to be linearly dependent. Okay. So if there exists no other solution other than this, then they are said to be linearly independent, and if they are not linearly independent, they are said to be linearly dependent. Okay. So we will give some examples of these, but before we go to the examples, I want to define these two other terms. The next is the basis. So a set of vectors, so the vectors I'll deliberately use the term vectors b1, b2 up to bn form a basis in the vector space if they satisfy two conditions. Okay. The first condition is that b1, b2 up to bn are linearly independent. So, I will use the term Li for linearly independent. Okay. So, all these vectors are linearly independent. The second condition is that any vector in the vector space can be expressed as a linear combination of b1, b2 to bn. Okay. And by linear combination, what I mean is exactly something like this, where you have some scalar multiplying b1 plus some scalar multiplying b2 and so on. So, any vector, suppose you have an arbitrary vector v, then you can express that as some scalar. I'll say c1 b1 plus c2 b2 up to c, where all these c1, c2 etc. are scalars. So, any vector in the vector space, okay, there should be no exception. Every vector in the vector space, that means every vector, each and every vector in the vector space should be or should be expressible in this form. Okay. So, and then these vectors, if it is so, if the set of vectors satisfy both these conditions. First, they should be linearly independent, and secondly, any vector in the vector space should be expressible as a linear combination of these vectors. If they satisfy these two conditions, then these vectors are said to form a basis in the vector space. Okay. Now, if you have a combination of vectors such that any vector can be written as a linear combination of these vectors, then these vectors are said to span the vector space V. Okay. So, when you say you have certain vectors that span the vector space V, what you mean is that any other vector in the vector space V can be expressed as linear combination of these vectors. Okay. Again I emphasize that we will come back and we will look at examples of this, but first let me define one more quantity, and you have seen all these before in different forms. So, but it is good to see the formal definition, so that you will be able to use these concepts even where even for other cases. Okay. So, the dimensionality is nothing but the number of vectors in the basis. Okay. So, if the basis set contains 3 vectors, then you say it is 3 dimensional vector space. If the basis set contains 4 vectors, you say it is 4 dimensional vector space, and so on. Okay. So, the number of vectors in the basis is called the dimensionality of the vector space. Now, with this definition of the basis, you can also show that the maximum number of vectors that can be linearly independent is the dimension of the space. You cannot have, in a 3 dimensional vector space, you cannot have 4 vectors be linearly independent. So, the maximum number of vectors that can be linearly independent is equal to the dimensionality of the space, and I leave this as an exercise for you to work out. Okay. So, let us now look at some examples of basis vectors. So, in the usual 3D Cartesian space, we have a vector that is x, y, z, okay, and any vector can be written as a linear combination. So, it can be written as a scalar x multiplied by 1 0 0 plus a scalar y multiplied by 0 1 0 plus a scalar z multiplied by 0 0 1. Okay. So, these vectors 1 0 0 0 1 0 and 0 0 1, they span the entire vector space. Okay. Now, the next question is, are these 3 vectors linearly independent? And it is easy to show that 1 0 0 0 1 0 and 0 0 1 are linearly independent. And again, I leave this as an exercise for you to try. You take a linear combination of these and you show that if that linear combination is 0, then each of the scalars multiplying these have to be 0. So, I leave that as an exercise for you to show. So, this is the first example. So, these are linearly independent and they span the vector space. So, 1 0 0 0 1 0 and 0 0 1, they are basis, or they form a basis in 3D space. So, 1 0 0 0 1 0 and 0 0 1 form a basis in 3D space. Okay. Next, let us look at another example. This is the vector space of all polynomials up to order 3. Okay. And so this in this vector space, any vector v is written as a0 plus a1x plus a2x square plus a3x cube, okay, where x is the variable of which we are taking the polynomial. Okay. So, the set of all possible vectors. So, if you take all possible vectors, you will get all possible polynomials up to order 3, and this forms a vector space. Okay. And now the question is, what would be a suitable basis for this vector space? And you can easily show that the vectors 1 x, x square and x cube. So, this vector, these 4 vectors, they form a basis for this vector space. You can easily see that 1 is a vector, because 1 can be written as 1 plus 0 x plus 0 x square plus 0 x cube. So, 1 implies a 0 equal to 1 and all the other 3 are 0, and so that is also a polynomial of well, not order 3, but it is less than or equal to order 3. So, it is order 0. X is also a polynomial of whose order is less than or equal to 3, similarly for x square and similarly for x cube, and you can show that any vector can be written as a linear combination of these vectors. So, this forms a basis, and you can also show that these are linearly independent. So, you cannot, if I take any combination of these, if I take C1 plus C2x plus C3 x square plus C4 x cube equal to 0, the only way this can be satisfied is if each of these coefficients is 0. So, the only solution is C1 equal to C2 equal to C3 equal to, or sorry, I should have C0 C1 C2 C3. So, C0 equal to C1 equal to C2 equal to C3 equal to 0. So, all of them have to be 0, and that is the only solution, because this is a polynomial in x, x can take any arbitrary value, and the only way this is satisfied is if each of these terms are 0, and that means each of the coefficients have to be 0. Okay. The other thing I want you to notice are that basis vectors are not unique. So, there are many sets of basis vectors that you can have. Okay. For example, in 3D Cartesian space, you can have this set of basis vectors, but you can also show that the vectors 1 1 0 minus 1 1 0 and 0 0 1, these also form a basis. So, in order to prove this, you have to show two things. First is that these 3 vectors are linearly independent, and the second part is that any vector can be written as a linear combination of these 3 vectors. And again, I leave this as an exercise for you to work out. So, you show how you can take first you show that these 3 vectors are linearly independent, which is relatively easy to show. Then the second part, you have to show that you can write any vector as a linear combination of these 3 vectors. Okay. So then what the important point is that the basis vectors are not unique. Okay. So, you can have many different set of vectors which form a basis. Okay. Now, notice that since we were dealing with 3D Cartesian space, okay, you can have only 3 vectors in the basis, since the dimensionality of the space is 3, since you have 3 vectors in the basis. In this case, the dimensionality was 4, because you have 4 vectors in the basis. Okay. So, the dimensionality of the vector space is equal to the number of vectors in the basis, and that does not change even if you change the basis. So, you can whether you use 1 0 0 0 1 0 and 0 0 1 or 1 1 0 minus 1 1 0 and 0 0 1, the dimensionality of the vector space remains the same. Okay. So, we saw that the vectors 1 0 0 0 1 0 0 0 1, these form a basis. So, these are the basis vectors, okay. And these 3 vectors span the entire vector space. So, we say that they span entire 3D space. Okay, so that means any vector in 3 dimensions can be written as a linear combination of these 3 vectors, and if you take all possible linear combinations of these 3 vectors, you will get all the vectors in the 3D space. Now, suppose you take the linear combination of just 2 of these vectors. So, you take a linear combination of, instead of the 3 vectors in the basis, you take a linear combination of these 2 vectors. Okay. So, if you take So then if you take all possible linear combinations of these 2 vectors, then you will span a subspace okay, the subspace of the 3D space, okay. And in this case this subspace is a 2-dimensional subspace. So, this is a 2-dimensional subspace. Okay. So, if you take a partial list of the vectors in the basis and you take all possible linear combinations of these 2 vectors, you will get a vector space, but that is a subspace of the 3-dimensional vector space. Okay. So, since you took only 2 bases, okay, this is a 2-dimensional space, and you can easily see that these 2 span the entire x y plane. So, they, if you have x, y and z. Now, these 3 span the entire space, entire 3-dimensional space, the x, y, z coordinates, whereas if you just take linear combinations of these 2 vectors, then if you just take linear combinations of these 2 vectors, you will get all the vectors in the 2-dimensional space. So, you will just span this plane, okay, and that is a subspace of this full 3-dimensional space.